what I want to do now is to show you some examples of the use of these various techniques to measure important reactions in the hydrogen-oxygen system. So just to remind you of this, these are the explosion limits. I won't go through this because we've just talked about it very recently. But the reactions that are significant are things like these branching reactions, H plus O2 going to OH plus O. This and the competition between that and this termination reaction, H plus O2 going to HO2. And reactions like HO2 plus HO2 generating hydrogen peroxide. There should be an O2 in there as well. So that's HO2 plus HO2 forming hydrogen peroxide plus O2. And then the dissociation of hydrogen peroxide. So all of these have been studied by a variety of techniques. And what we'll do now is to have a look at the data. First of all, sensitivities. Now, I realize that not all of you understand what a sensitivity is. For example, here we're looking at the sensitivity of the ignition delay time to these various rate constants, these various reactions. And so if the ignition delay time is, let's call it T ignition, then the sensitivity is going to be something like T ignition versus dT ignition divided by a rate constant, a specific rate constant. Actually, it would probably be a normalized one, so it would be d log T ignition by d log K. So that's what we mean by sensitivity. And you would generate these sensitivities from the modeling that you do. And so what's happened here is that Jim Miller has done a model of an ignition delay time using a mechanism, hydrogen-oxygen mechanism with a set of rate constants, good rate constants in it, and then he's determining these sensitivities for the various reactions. And what you can see, and these are different temperatures, 500K, 900K, 1100K, 1500K. And you can see the extreme sensitivity at low temperatures with respect to this branching reaction, H plus O2, but also high sensitivities, especially at somewhat higher temperatures, with respect to this termination step. So those ignition delay times are being extended so they're made longer by this reaction and shorter by this reaction here. And one of the other important sensitivities relate to the reaction between H and HO2. As we said, H is a chain carrier. HO2 is quite a slowly reacting species. And here we've got H plus HO2 forming two OHs, so we get a positive, we get a negative sensitivity over here because it's shortening the ignition delay time. This is H plus HO2 producing H2 plus O2, so removing a chain center, producing stable molecules. So that's a positive sensitivity, extends the ignition delay time. And then this third reaction, again, converts OH into O, and that's got a small negative sensitivity. So these are key reactions as well as these others.
We just set the rate constant to 0 for a particular reaction to see its sensitivity. Is that it?
No. It's a bit more subtle than that. You vary it slightly. So what you do is you look at the ignition delay time and you slightly increase or decrease the rate constant and run it again.
Within a range.
Within a range. So maybe changing it by 10% or something like that. Okay? So this is a whole set of determinations of H plus O2 going to OH plus O, and they're mainly high temperature measurements, and these are all shock tube measurements. Someone asked, when do you use the different techniques? Shock tube measurements are especially valuable at higher temperatures. You can extend them to low temperatures below 1000 K, but their main value is looking at higher temperatures. Whereas pulse photolysis it's very difficult to use the technique above about 1000 K, and so that's used in the lower temperature region. So these are all shock tube measurements, and you can see these measurements extending from 3000 K to 1100 K, and this is an analysis by Hong et al. In 2010, which have been reanalyzed by Michael Burke, and this is an important paper that looks at a lot of these different reactions. And we'll talk about evaluation in later lectures. Now, I mentioned those experiments using a flow technique to look at O plus OH. Now, O plus OH, and these were all done at low temperatures, 150 to 500 K. These measurements in this reaction in itself is not important in this temperature region as far as combustion is concerned. It's far too low. But the important thing is this is the reverse of that branching reaction. And so what you can do is you can use these data, combine them with the equilibrium constant, and get a wider range of measurements for the reverse reaction H plus O2. So you can use these radical-radical reactions, O plus OH, to extend your information base on H plus O2 by calculating the rate constant using the equilibrium constant. And so that rate constant is now defined over a range 250 to 3000 K. There's the best fit value for the rate constant. And the uncertainty in it is of the order of something like plus or minus 50% over that range. Here's the second branching step, O plus H2 going to OH plus H. Again, measurements at high temperatures using shock tubes by Sutherland, monitoring O by resonance fluorescence and generating it by flash photolysis. Davidson and Hansen used generated O by laser flash photolysis and also by pyrolysis, and they monitored the O by absorption spectroscopy. ARAS is atomic resonance absorption spectroscopy. And then a set of measurements, again using the same technique down here. And you can see that the rate constant is reasonably well defined over this quite high range of temperatures. H plus O2 plus N. So this is this termination reaction. So what happens is this is in competition with the branching step. It forms HO2, an energized HO2, and you need a third body there to stabilize the HO2. It acts as a route to branching through the formation of hydrogen peroxide at higher temperatures. And the reaction is at the third order limit, except at very, very high pressures. So if you remember, we look at the rate constant as a function of m And it looks something like that. We've got K infinity up here, and the rate constant down here is K0 times m. And it's very much in this reaction operates very much in that low pressure region because the molecules are quite small. I'll try and explain why that is when we talk about theory tomorrow. So Michael et al. Used flash photolysis at room temperature for a wide range of third bodies and shock tubes at higher temperatures for these third bodies here. And so they're getting data over a very wide range of temperatures. And one of the things that they found was, and this is now really well established, is that water is an unusually effective third body, M. So if, and this is important to recognize in combustion systems because the water concentration is often relatively high, the order of 10% or something like that. So stabilization by water is key. And so there's a reminder of this fact that we're operating in this region here, low pressures, and what's important is K0m. So those are the measurements, different third bodies. Here's a set of measurements with water as the third body, showing unusual efficiency. In Germany, they did some, this is at Göttingen, they did measurements at really very high pressures. So these again, are difficult experiments to do. So they're pulse photolysis experiments. And so this is a high-pressure cell with steel discs, very, very thick windows. And they're going up to pressures of something like approaching 1,000 bar. So these are really pretty high pressures. They generated H from the photolysis of ammonia at 193 nanometers, and they operated from 300 to 900 K. And they detected HO2 by absorption spectroscopy. So they sent light through the cell and then used a monochromator to select a particular wavelength where they could detect HO2. And the particular wavelength was 230 nanometers. And at these higher pressures, the reaction moves out of this third order region into this region further up here. And so this is an example of the measurements that they made. H plus O2 reacting to form HO2. And they're detecting the HO2, and there's the production of it. And these are different temperatures and different pressures. Okay, so these are the ranges of temperatures here and different pressures. And you can see that it's no longer linear in argon, but it's beginning to approach the high pressure limit. It's got still a long way off, but beginning to approach it. Now, one of the things that they can do is that if they normalize the rate constants to and the low pressure limit to K infinity, so if they take K0 and there should actually be an m in there, so that's K0m divided by K infinity, and this is K over K infinity. If they normalize them in this way, then all the curves, different temperatures, different pressures, different third bodies, all lie along the same reduced curve. The only trouble is you need K infinity to do this, and this requires a calculation of the high pressure limiting rate coefficient that isn't available experimentally. So they have to calculate that separately. But the nice thing is that this gives you a single representation in this reduced form for this rate constant essentially as a function of pressure. But if you could just insert a concentration of m in there, that should be K0 times m. It arises because they have a slightly different way of defining K0. And again, this important paper by Michael Burke in the International Journal of Chemical Kinetics looks at these measurements from different sources and makes recommendations based on this Troy fitting process. If you remember, there's the Lindemann-Hinshelwood expression modified by this fall-off parameter f, which depends upon f cent, and they then fit the data in different ways. There is another alternative. There is an alternative to the Troy method, and this is what's called the P-log method. Has anybody used the P-log method? No. Yeah. Okay, so someone has. And basically what you're doing is you're using a polynomial representation. You've got various measurements of the rate constants and use a polynomial to represent the pressure and the temperature dependence. And then you use an interpolation method to go between different pressures. So these are three different pressures, a polynomial representation of the rate data, and then interpolating between those different pressures to get a rate constant at a specific pressure. The great thing about it is it's very, very flexible. And it's been incorporated in ChemKin, and it's already programmed in there. So you can take your data and you can represent them in this way. Or alternatively, if you have this representation, you can put them into a ChemKin program. One of the things that we'll look at tomorrow is just how good theory is getting at representing these things. This is actually quite a complicated reaction, H plus O2 plus M. And so what we've got here are various experimental measurements. These experimental measurements here at a particular temperature as a function of pressure. Sorry, these are the reduced curves again. So this is a wide and total set of data. And the red curve is a fit using theory, but fitting the theory to the experimental data. The blue curve is just a straight fit to the experimental data. And then the black one are calculations that have been done by Stephen Klippenstein, and those don't use the data at all. This is an ab initio calculation directly calculating this rate constant. And you can see how good it is. It agrees with the experimental data really remarkably well. And so that's using theory without fitting, using theory directly to generate the rate constants. Okay, now this reaction is more of a problem. This is HO2 plus HO2 going to hydrogen peroxide plus oxygen. And what happens is that at low temperatures, it depends upon pressure. I haven't shown the pressure dependence there, but it does depend upon pressure. And so what's happening is the HO2 and the HO2 come together. They're stabilized. They come together to form H2O4. That's stabilized, and then it dissociates to form HO2 plus HO2. Sorry, H2O2 plus O2. And the rate constant for that decreases as the temperature goes up. So the rate constant goes down as the temperature goes up. And then it starts to turn around. And what's happening here is it's basically a direct abstraction reaction. Instead of going through H2O4, one HO2 is abstracting an H from the other HO2, forming hydrogen peroxide. And that gets faster as the temperature increases. The only problem is there are two sets of measurements. So this is one set of measurements, and the upper line is another set of measurements. And they disagree really very, very substantially. And in that analysis by Burke, he said it's difficult to discern which, if any, of the high temperature determinations is reliable. So there's a considerable uncertainty in this rate constant in this region up here. And we'll return to this reaction tomorrow when we talk about theory, because theory does shed some light on this problem. But it's an important reaction, and especially in this higher temperature region, because it's the way in which hydrogen peroxide, or one of the ways in which hydrogen peroxide is generated. And remember, hydrogen peroxide dissociates at high temperatures to regenerate OHs, and that's the way in which that third limit comes into play. Right, now we form the hydrogen peroxide. Can we say something about the rate constant for hydrogen peroxide dissociation to form hydroxyl radicals? And this is the branching step at high temperatures. And there's an analysis by Troy in this issue of Combustion and Flame in which he looks at the relationship between the thermal dissociation and also the recombination. So using the equilibrium constant, we can relate the forward rate constants and the backward rate constant, or equivalently, we can measure the forward rate constants, we can measure the backward rate constants in different regimes and put them together to have a better understanding. So the reaction's far from the high pressure limit, and to obtain his representation, Troy needed to get a value for K infinity, which he did by calculation. He used a technique of his called Statistical adiabatic channel theory to calculate this equilibrium constant using an ab initio potential energy surface. And as I said before, important thing is the use of thermodynamics to get the forward and reverse rate constants. As we'll see actually it's going to be Thursday, there's been some uncertainty in the enthalpy of formation of OH, which has been changed quite significantly in relatively recent years. And so bear this in mind when we come to discuss that. So there's the association reaction, flash photolysis coupled with laser-induced fluorescence going to really quite high pressures and not getting close, really, to the high-pressure limit. The reaction's second order and radical, and so the absolute concentration is needed. So quite difficult experiments, especially given they're going to these relatively high pressures. So that's about 100 atmospheres there. And here's the dissociation reaction using a flow reactor and static studies at lower temperatures and also shock tube measurements above 950 K. So these are experiments going from 950 K to 1250 K using shock tubes to measure this dissociation reaction. And then the dissociation and association data are fitted to a Troy expression, for example, or using p-log. But in this case, they use the Troy expression using the theoretical high pressure limit and equilibrium constant to put everything together. And so that's the data for H2O2 dissociation determined in this overall way. Okay. Right. Any questions? No. So this is HO2 plus HO2?
Yes.
Yeah. Well, it all depends on what you mean by an elementary reaction. So what happens is that HO2 plus HO2 come together to form H2O4, and that can just go back out again unless there's some stabilization to form H2O4 more stabilized, and then that H2O4 can fall apart like that. Now, to me, that's still an elementary reaction, but we'll argue about this tomorrow. Yes, it would be nice to know what you think about that. But the alternative is that HO2 plus HO2 simply abstracts this hydrogen. And so that's going over an energy barrier. So they're two different routes to the same products.
So is one more prominent in different temperatures?
Yeah. So this one is prominent at low temperatures, and that gives rise, so if you look at the rate constant versus temperature, it looks like this. I'll produce some more. I'll produce some more data that shows the pressure dependence. That would be helpful. So it depends upon pressure, and so this is the rate constant decreasing with temperature, with increasing temperature, and that's this mechanism here. And then what happens is the other mechanism takes over, the direct abstraction mechanism, and that applies at high temperatures. So the direct the barrier is too high to be operative down at these lower temperatures, and at these higher temperatures, it's beginning to dominate what's going on, and the mechanism essentially changes. Does that answer your question? Okay. Right. What we'll do now is look at theoretical methods for calculating rate constants. So we're still worrying about calculating rate constants for specific elementary reactions. And this is using theory. And there are a number of theoreticians in the audience, and I hope they will help me out where I get things wrong. Yeah.
So the HO2 mechanisms that you were talking about, where we produce HO2 to produce peroxides, is typically used to explain like low temperature chemistry for hydrocarbon fuels. So is it true that for any hydrocarbon combustion, you would still have these reactions, these intermediate steps, which would actually show the low temperature chemistry behavior? Because, like, for example, methane, combustion of methane, does it still exhibit these low temperature chemistry behavior?
Yeah.
Okay.
Yeah. I mean, less extensively. I mean, for methane, it's a relatively high temperature process, but you can still get those peroxyradical processes, but you don't get the general the usual autoignition processes because you've only got a single carbon atom. So the formation of hydroperoxides is not straightforward. But for ethane, you get autoignition chemistry. For heptane, you get autoignition chemistry. Yeah. Okay, so a theoretical basis. So let's make a start on this, and then we'll come back to it tomorrow. These are quotations from Stephen Klippenstein, and this is a plenary lecture that he gave at the Combustion Institute, the Combustion Symposium in 2016, published in 2017. And so let me read this out because it's important. The accurate prediction of the temperature and pressure dependence of gas phase reactions requires state-of-the-art implementations of a variety of theoretical methods: ab initio electronic structure theory, transition state theory, classical trajectory simulations, and the master equation. Future progress in the fidelity of the chemical modeling of combustion will benefit from more widespread applications of theoretical chemical kinetics and from increasingly intimate couplings of theory, experiment, and modeling. So Stephen is arguing that theoretical chemistry has made great advances and it can make contributions on its own, but in addition, it will make even greater contributions if we link it to experiment, but also if we link it directly to simulations of combustion systems. So that's what he means by the modeling there, modeling of combustion systems. And this is a slide taken from a paper by Fei Qi in Science China, and it's a modification of a paper by Ed Law, which shows a series of combustion mechanisms. So this is methane oxidation going up to much more complex systems, biodiesel, C16 chemistry, C12 chemistry, and so on. And it shows it as a function of time, okay? And few mechanisms generated since 2010. And the important point about this slide is that there are tens of thousands of species and tens of thousands of reactions. So some of these mechanisms are incredibly complicated, and they involve many, many reactions and therefore many, many rate constants. Speaking as an experimentalist, there is no way in which one could make those measurements directly. You can measure some of them and use those to help understand with the help of theory, but theory is absolutely essential for determining some of them, a lot of them. And various theoretical methods that some of you know very well to generate rate constants automatically for complex systems. So that's something to bear in mind, the size of these mechanisms and the fact that calculation is going to be essential to determine some of these rate constants. So what we're going to do is we're going to look at potential energy surfaces for stable molecules and for reactions. We'll look at theoretical methods for determining these potential energy surfaces. We'll examine the basis of transition state theory, treatment of reactions with no or small energy barriers using variational transition state theory, as well as high barriers using ordinary transition state theory, reactions with two transition states, and then pressure-dependent reactions and reactions involving multiple wells using what are called master equation methods. Now, some of that may not mean a great deal to some of you, but hopefully by the end of tomorrow it will. So a reminder of statistical mechanics that we talked about yesterday. If we take this generalized reaction here, nu I is the stoichiometric number, xi is the species, and reactants have got negative stoichiometries, products have got positive stoichiometries, and we sum them all together and set that equal to 0. And the equilibrium constant for that system is given by this expression here, where we've got the partition function for the ith species divided by the volume. If you remember, the volume is included in the partition function, but to get the equilibrium constant, we have to divide by it. And for Q over V, we use the symbol big Q. So this here is big Q. And delta E naught is the difference in 0-point energies of the products and the reactants. And exactly the same equation is used in the formulation of transition state theory. So transition state theory is set up using exactly the same formulation. So this is a brief discussion of transition state theory in advance of what we'll talk about tomorrow. So here are the reactants, A and B, C, the transition state, A, B, C, with an energy delta E naught relative. So that's the energy of the 0-point levels of the 0-point level of the transition state relative to the 0-point level of the reactants. And the rate constant is given by a parameter alpha multiplied by KT over H. Q, that's little q over V for the transition state with a little dagger on it, and QA and QBC, the partition functions of the reactants, and then e to the minus delta E naught over KT. This sign here indicates that one mode of motion, which is motion along the reaction coordinate, which I'll define later on, has been removed from that partition function. And it's actually the origin of the KT over H term. So this will become more obvious when we look at the potential energy surfaces. Once again, don't confuse the K terms. This K in here is the Boltzmann constant. That's the rate constant. That's the Boltzmann constant. So apologize for using the same term, but it should be obvious which means which. Alpha is a correction factor, and its most common source is from the incorporation of quantum mechanical tunneling through the barrier in H-atom transfer reactions. So as we mentioned yesterday, because of tunneling, you don't necessarily need to go over the barrier. You can go through it with reduced probability, but nevertheless with less energy if you're transferring a hydrogen atom. We can also formulate the transition state theory using thermodynamics. So another way of representing this equilibrium constant is as e to the minus delta G standard over RT. And so we can also, there's the transition state theory representation. We can represent it in terms of delta G dagger, which is the Gibbs energy of activation. So that incorporates an enthalpy term, an enthalpy of activation, and also an entropy of activation. And that's often quite a useful concept to bear in mind, and we'll discuss it when we talk about variational transition state theory. The Born-Oppenheimer approximation. Electrons are very light, and they move around very quickly. Nuclei are much more massive, and they move more slowly. So what we can think of is the nuclei sitting there, and the electrons are buzzing around, and the electrons interacting with themselves and with the nuclei are generating a potential energy for that particular configuration of the molecule. If we move the molecule, then the electrons will readjust, and the potential energy that exists will then be somewhat different. So that's the idea behind all this. Electrons are very quantum mechanical or wave-like, described by the Schrödinger wave equation. Atoms and nuclei are much heavier, move much more slowly. So what we do is we solve the electron motion problem first, assuming that the nuclei are stationary, and at a specific geometry R, that's not right, are stationary at a particular geometry R, and yield a potential field V of R that the nuclei are moving in. And then we determine this V of R, and then we change the position of the nuclei and determine a new V for the new R. Let's remind you about molecular degrees of freedom. We said something about this briefly yesterday. Molecules composed of n atoms has got 3n nuclear degrees of freedom. So each atom can move in 3 different directions. And for n atoms in a molecule, where they're moving relative to one another and constrained to stay relatively close to one another, 3 of those are translation, 2 of them are rotation for a linear molecule, and 3 of them are rotation for a nonlinear molecule. And that leaves 3n minus 5 vibrations for a linear molecule and 3n minus 6 vibrations for a nonlinear molecule. The interactions between the electrons and the nuclei provides the potential energy surface that defines the equilibrium geometry of the molecule and the response to the relative motion of the atoms, the vibrations and the internal rotations. What happens is the molecule is vibrating from its equilibrium position, and as it vibrates, the interactions with the electrons change, and so the potential energy changes and increases. And molecules described by the Born-Oppenheimer principle, which allows us to say the total wave function is going to be a product of an electronic wave function and a nuclear wave function. There are some interactions, but this, by and large, is a very good approximation to make. Let's have a look at potential energy surfaces. So this is the potential energy surface for a diatomic molecule. So what happens is there is an equilibrium position here where in which the energy of the molecular system is obviously minimized, and then the molecule vibrates and the potential energy increases. And as it vibrates, then the range of vibrational the range of the vibration increases, and also the energy that's involved, the potential energy that's involved increases as well. And as we increase the amount of vibration we put in there, eventually what can happen is the molecule can dissociate. What we talked about when we discussed vibration yesterday, we talked about a harmonic oscillator. So we drew a curve that looked like this, and the energy levels, we said, were equally spaced. So that's a harmonic oscillator. But a real molecule is anharmonic. And so what's happening is this curve here extends like this, and then the molecule can eventually dissociate. And that affects the energy levels. What we said was the energy levels are evenly spaced. We can write those energies. So the energy of the V level is given by V plus a half HC omega. And we'll put a little subscript E on there. And that gives us evenly spaced levels. But for an anharmonic oscillator, we get extra terms coming in. Where this is what's called an anharmonicity constant. And these are going to become more and more important as V increases because it's a squared term that's there. And this is an important consideration in terms of the calculations of rate constants. Okay, but that's just demonstrating what's going on for a diatomic molecule and just defining the vibration is anharmonic because the molecule dissociates if sufficient energy is incorporated. As a result, the energy levels are not evenly spaced, but converge. And the 0-point energy is h nu over 2 for a harmonic oscillator, slightly different for an anharmonic oscillator. And that allows us to define two different dissociation energies, one coming from the bottom of the well here, and one coming from the 0-point energy there. And it's important when you're doing calculations and you're tabulating energies to define whether you're referring them to the 0-point energy or to the bottom of the potential energy well. okay, this is just a reminder about vibrational energy levels, and they depend upon this restoring force here, and depend essentially on the curvature of this potential well down here. And from that curvature, if you calculate that curvature from the potential energy surface, then what you can do is you can determine the vibrational frequencies. Rotational motion is slower than vibrational motion and depends upon the moments of inertia, and hence on the average bond distance. And so the rotational energy levels are determined by the bond distances that you determine from your potential energy surface calculation. Normal modes of vibration, we said there are 3n minus 6 vibrations for a nonlinear molecule, 3n minus 5 vibrations for a linear molecule. This, for example, is CO2, C and 2 O's. It's a linear molecule, and there are 3 vibrations. There's a symmetric stretch, that one, an asymmetric stretch, that one where this bond is compressing, that one's extending, and then a bend, which is doubly degenerate. It can vibrate in the plane of the board, or it can come out of the plane of the board. And these are called the normal modes of CO2. And we need to know the frequencies of those normal modes in order to do our calculations. Water is nonlinear, and so should add that this bend is doubly degenerate, and so that gives us our 4 vibrations. 1 vibration here, another vibration there, and 2 vibrations in there. Water is nonlinear, and so that has 3 vibrations, this symmetric stretch here, a bend, and a complicated asymmetric stretch over here. So symmetric stretch, bend, asymmetric stretch. Now, just let's have a look. We showed a potential energy surface for a diatomic molecule. Let's have a look at what it looks like for a polyatomic molecule. So this is a triatomic. I'd find it hard to do anything more complicated than this. But there's one bond distance. There's the other bond distance. So this could, for example, be CO. Well, it is CO2. And there is a third dimension, which is the bend. But we're keeping that angle constant in this case. So let's keep it constant at 180 degrees. Whoops. And so this is a potential energy well down here. And there's the equilibrium configuration for CO2. So there's equilibrium CO2. And if we look in this direction, then we've got a potential energy that looks like that. We're sitting at the minimum of the potential energy. And if we look in that direction, again, we're sitting at the minimum of the potential energy. This direction here corresponds to R1 increasing and R2 decreasing. So this is the asymmetric stretch. And vibration along there corresponds to the symmetric stretch. And we've got this potential well here. And if we give it more and more energy, then it will dissociate into O plus CO, or O plus CO over here. If we get it even more, if we go along the symmetric stretch and put more and more energy into the symmetric stretch, then what can happen is we can eventually, at much higher energies, generate O plus CO plus O. Okay, now, one of the reasons that I wanted to show you this slide, and we'll come back to it first thing tomorrow, is because it allows us to understand the potential energy surface for a reaction. So once again, let's have a look at a triatomic system, A plus BC. And this is what the surface looks like now. So quite similar to what we had on the previous slide, except we don't have a well here. If we go along from the reactants to the products, this is a maximum. Okay? And so this is the transition state at the maximum in the potential energy surface. On the other hand, if we go in this direction, we're sitting at a minimum, like this thing here. So the energy increases in this direction, energy increases in that direction. So the symmetric stretch for this ABC molecule, the transition state is ABC. The symmetric stretch where both bond distances are increasing at the same time is a normal vibration. But the asymmetric stretch is not. The asymmetric stretch corresponds to passage along here, and this is called the reaction coordinate. Okay, we're going from the reactants to the products, and passage along here is called the reaction coordinate, and there isn't a restoring force as there is in a normal vibration when we get to the maximum up here. Okay, well, we'll go through this again tomorrow, these last two slides, and then we'll go on and discuss transition state theory in a little bit more detail. But thank you for your attention.